Hello everyone. Previously, we have learnt on how to design axially loaded column. As have been explained in lecture video part 1, it is very unusual cases. Column will be carrying axial loaded alone. Therefore, in this video, we will learn on columns subjected to combined axial load and bending moment. Members with axial load and bending moment are also called beam columns. These forces can arise due to 1. Eccentricities in pinned connections of a simple construction design, or 2. End moments in rigid connections of a continuous construction design. For example, minimum eccentricities in a column of a simple construction design may be rises due to beam on a cap plate. The load of a beam supported on a cap plate should be considered to be acting at the face of the column towards the span of the beam. This is what we call as eccentric moment. 2. Roof truss on a cap plate. The eccentricities of a roof truss supported using simple connections may be neglected as no significant moments were developed. A concentric axial load may be assumed at this point. Thus, causes the column to be designed as an axially loaded column. 3. Stiff support. The load of a column with a stiff support may be considered to be acting at the midface of the support's flange. D. Simple bolted connections. In all other cases, the eccentricity of loading should be taken as 100 mm from the face of the column, or at the center of the length of stiff bearing, whichever gives the greater eccentricity. The picture shows the plan view of the beam column connection, where T equals web thickness and R1 and R2 are the end reactions of the beams. This figure shows the distribution of bending moment in a simple design, in which the moment for a particular floor is being distributed proportionally based on the column stiffness, as highlighted in the red box. Moment in a continuous construction design can be obtained from frame analysis. Some common loadings that give rise to bending moment in the continuous design are a. Unbalanced gravity load, b. Wind loads, c. Horizontal forces. Note that the gravity, wind and horizontal forces are applicable in both simple and continuous construction designs. It is in the latter approach that bending moment is induced in the frames to resist these loads. A column in a continuous design can thus have large bending moments. Figure illustrates the principal axes of a typical I-section of a compression member. Other members' shapes can be similarly drawn. Strong axis is a ZZ axis, and weak axis is a YY axis. Buckling is a two-dimensional, planar event. In other words, it happens in a plane that is perpendicular to the axis that it happens about. Figure shows planar views of the two principal planes for the I-section. This figure shows a column subjected to an axial force, major and minor bending moments. The left figure shows an in-plane buckling of a column in its weak axis, while the right figure shows the out-of-plane buckling of a column. Can you differentiate what is the difference between in-plane and out-of-plane buckling? Given here are the design process that must be carried out for a column subjected to axial and bending moments. Strength classification. A circumflex euro, in which the details information are given in Table 3.1, EC3-1-1 section classification. A circumflex euro, in which the details information are given in Table 5.2, EC3-1-1. The resistance of cross-section to combined effects can be found in Clause 6.2.9, EC3-1-1. And finally, the guideline on buckling resistance of member due to combined effects can be found in Clause 6.3.3, EC3-1-1. Note, as a conservative approximation for the cross-section compression resistance of Class 1, Class 2 or Class 3 cross-sections due to the combined axial load and bending moment, the following may be applied. Clause 6.2.17, EC3-1-1. OK class, next video will be on example regarding with a column subjected to axial and bending moment.